I'm starting these 3 courses, fine-tuning, RAD, and this. If you have colleagues in your workplace who would be interested, please spread the word. All right, guys, welcome back. In the morning, or in the prior to now, we covered CNNs in considerable depth. We saw how CNNs, they have an inductive bias that emphasizes locality of the features, hierarchical nature of features. It has built into the inductive biases translational invariance. You could see that. You move the eyes from here to here, representation also moves. So it still remains the same representation, just changes location. And these things align with how vision takes place in, for example, in human beings and cats and so forth. It's a good thing to do. And this was a good example of baking real life or things into the neural architecture. Very successful run for the CNNs. It's an amazing industry workhorse. The CNNs are still a very dominant architecture. But we also started this course with transformers. As transformers started from the end of 2017, December 2017, gradually by 2018, 2019, people realized that transformers are not just efficient means to do things faster than recurrent neural networks. There's something fundamental about it. This whole concept of self-attention, it helps it understand language at a deeper level. So people ask this question: if it understands language at a deeper level, can we apply it to images? First of all, the CNNs are massively parallelizable, but transformers now, they didn't have the bottleneck of RNN. They also can do computes pretty fast and in parallel, though are more expensive compared to CNNs. They're far more expensive. Why? Because of the quadratic cost of attention. Remember, it is softmax of k dot q. Prefixing, that's the attention score, is k dot q, which is a quadratic compute. And nevertheless, people asked, if you built some sort of a visual model with transformers, is it possible? Would it be better? Can you do things? This is the sort of question that was being asked at Google Research. And the result was this paper, the vision transform. And it was published in 2021. Though I think, in the early 2021, the things were still already coming in, that it could be done. These people had figured it out. I think that, why do I remember the data as more like early 2021, but I may be wrong. So I'll go over this paper carefully. So again, what's the motivation? The motivation is, if the transformer architecture is really so good at understanding language, and images are a visual language of expression, then it is worth leveraging the transformer for vision tasks, image segmentation, image classification, etc., and seeing how well it does. Does that make sense? You will know only if you do it. The whole question was, how would you do it? For language, there are words, there are sentences. But what about image? Okay. And so I'll give you the core idea of how they came upon this breakthrough thing. What they said is that if you treat the image as a sentence, the whole image as a sentence, the only question worth asking is, what are the words or tokens in the sentence? Isn't it? So for that, what they did is, let's say we have an image. And our image of sunrise. And here's a tree growing. And here's a river flowing. Right? Now, what they what the suggestion was is what happens if we take this image and we slice it up into 16 pixel cross 16 pixel. What are each of these things are called patches. Patch. And you treat each 16 by 16 as a word. You say, but nobody has heard of, there are multiple problems with this. First of all, in which there is no English word. Right? This is not a word, but that is easy to overcome. They say that, you speak English, I speak some other language, right? My words are different from your words. Then you can say, okay, all right. But what word is it? Where's the vocabulary? Right? Because words are taken from a finite vocabulary, right? English dictionary or something like that. What about these words? Because, a picture can take any form. 16 by 16 pixel admits many possibilities. And what they are saying is that not really. Well, 16 by 16 is, how many pixels is it? 256. Yeah. If each pixel can take, let's say, 255 values, well, 256 times 255 is your total vocabulary size. Right? So you do have, in some sense, a finite vocabulary. Right? And so if you have a finite vocabulary, theoretically, you can map each pixel to a embedding vector, word embedding, isn't it? And the best part is in Transformer, the word embeddings are learned. You don't use word2vec or anything. You basically say, given this input, what is the best embedding? The Transformer learns through backpropagation anyway. And that was the key insight. They realized, oh, we can do it. And not only that, how the embeddings are generated itself is learnable, right? By throwing gazillions of images at this machine and pre-training this machine. So if you understand that, you pretty much are looking at what in hindsight became yet another profound revolution. See, think of a simple BERT architecture, a BERT. Do you remember what a BERT was? It was just the encoder part of the transformer, right? What would you do? You would put a CLS token in the beginning of the sentence, right? So it would be CLS followed by all the words. Okay, or more specifically, because they're word pieces, etc., tokens. Right? That's what you had in BERT. So what they're saying is, let's do exactly the same. Exactly the same. The key insight is you break it up into patches. So now you have put all the patches in a sequence. You will need position embedding, of course, where the patches, but then you do a linear projection to flatten them make them into a vector, right? So it's a projection matrix, right? How do you take? So suppose I have a vector, let us say 16 cross 16 vector. How do I flatten it? All you do is you multiply it with something, okay, cross 1. Let me take another color. Isn't it? So you just have a linear projection. And then if you want to boost up its size, etc., you can do all sorts of magic that you want, right? So you could play these games. You can do linear projection of flat. And then once you had the flattened patches, or you could do something else. You could just first linearize it and then do another projection into some other dimensional space. For example, now that I have this, I can always multiply it with something else, transpose it, and multiply it and convert it to a M, like a column vector of, instead of 16, all the way M dimension, right? Because in transformers, you usually put slightly higher dimensional vectors. I can do one more projection transformation, isn't it? Flatten it, do the transformations, and so on and so forth. Flattening is as simple as reading. Remember that You read this line, then this line, then this line, then this line, and so forth. And then you do a projection matrix. So anyway, those are small pieces. The bottom line is you can do it.
The projection part can tell it again.
Projection in
256, right? 16
yeah.
into 16.
Yeah.
That's when you flatten it, 256.
Yeah.
Okay.
See, here's the intuition of projection. Suppose you have three-dimensional space, right? And this is the floor of the three-dimensional space, right? So this is the floor. Suppose I have a vector, big vector. This vector will cast a shadow if I shine the light from the top. It will cast a shadow, isn't it? And the shadow will look somewhat like, does that look right?
Yeah.
This is the projection. So a projection of a vector. So now let's generalize it. Let us say we have the vector. Let me call this vector A, and let's call this vector B. We have a vector A, which belongs to three-dimensional space. B is the projection of it in two dimensions. Are we together? But now there is no, now what happens is here you can say, well, that was easy. I can just ignore the Z dimension, right? If this is the X, Y, Y, Z, you say, well, that's easy. What is so big deal about it? All you're saying is forget the Z. And then you'll get a two-dimensional vector in the floor. But suppose this was not aligned with XY. Suppose the plane was at a tilt. And I'm asking this question, this vector, what is the projection of this vector on this plane? Right? I could ask that question. And when you ask that question, you are taking a three-dimensional vector. Let's say that the initial coordinates of the vector was AX, AY, AZ. Right? What you are basically saying is, how do I convert it into a 2D vector? Right? So I need to convert it into BX, BY on that plane, tilted plane. Now, you can convince yourself that you can do it with a 3x2 matrix. Right? You have to do the transpose of it, multiply it with the 3x2 matrix. In general, it will do. So we have generalized. We have said that a matrix cross 2 matrix will project a 3 vector into a 2 vector. But now here's the other part of it. You can actually project up also, because a matrix has an inverse. So you can go from a 2D matrix to a 3D matrix, isn't it? So more broadly, any vector, so more generally, because you can go from low dimension to high dimension, high to low, all it is a matrix, isn't it? So for example, a two-dimensional matrix, if I multiply it by 2x10 matrix, what will it do? I will get a 10-dimensional matrix. The other way around, right? So more generally, a matrix multiplication will project, multiplication of size m cross n will project a vector m to a vector in R. Right? So these matrices, therefore, are projections. Their quality is they're linear transformations, right? They're always considered linear. There's no activation or anything there. So whenever you see the word projection used in our field, always assume that it's a linear matrix transform. Are we together? It's just a matrix multiplication. And most of the time you do projection because you want to align the dimensions. Because, you know, your encoder, for example, if it is a bird, it is expecting, if I remember right, a bird is expecting a 300 or 300 dimensional or something like that input vector. Your patch is not that, right? So it is only 256 dimension, something like that. So what do you want to do? You want to apply a projection to align it with bird. Now do we understand that? So that's the linear projection part of it. Then you add the embedding, position embedding, which you always do. Then pass it through the transformer encoder. In this particular case, they passed it through a bird, I believe. Similar to bird, class token we prepare. So they basically did something very, very similar to bird, same CLS, etc., etc. Position embeddings are added. And you notice that something interesting, and you early on begin to see it, the activation function they're using in the feed forwards in the final layer, multi-head. So what happens is that from the transformer, a hidden state will come out, isn't it? For the CLS. They want to do some further MLP heads, like multi-layer feed-forward heads. You always put it through a few feed-forward heads after the attention heads. The advantage of doing that is two advantages. First of all, you might as well do it because your last layer will be a softmax made up out of whatever number of things. See, ultimately you're saying, I'm recognizing this image. Is it a cat or a dog? So then your softmax will have two layers. But if I have 10,000 objects to choose from, it will have 10,000 softmax layers. So before that, so that itself makes a layer, but you add typically a couple of layers more. Why deep layers prove very useful in adding at the end? We are only beginning to understand fully. Amongst other things, we are finding that these feed-forward layers, the simplest thing, they are, in some sense, the parametric memory bank of networks. That's where it stores its learnings. Right? It's quite interesting. We are beginning to get a clue why it is a good idea always to, before the output, throw in a few feed-forward layers. Some you have to, but the fact that they also lead to better results. Now, this part of it is standard. What you are seeing on the right-hand side where my mouse is classic transform, classic encoder, isn't it? Nothing different. If you look at the picture of the attention is all you need paper. This is what it is. You take this and you stack it L times, one on top of the other, right? And when you do that, I think they must have told what the value of L was, how often that time. But I think in the original work, it was 6 or 12, if I remember right. Right. So anyway, those are small details. And when they did that, the whole question was, will it work? Because see, you're giving up many things. The convolutional networks benefits from a lot of it. Inductive bias, locality of features, translation equivariance, because of pooling, insensitivity to minor perturbations, hierarchical features, all of those things. And it's a thought that, okay, can transformers even work or do as well as CNNs can? That is the main question you would ask, isn't it? If you tried this. So let's look at the results. What do the results speak? So I won't go through the way. So yeah, they explain what the values were, what variations they took. They use the Adam optimizer. Remember, we talked about the Adam optimizers in the intro to AI course. So that should look familiar. So when you see Adam, it's not Adam and Eve. So we first compare our largest models, so 14 and 16 layer head, and to state-of-the-art CNNs from the literature. So look at these results. At that time, the state-of-the-art CNNs were the ResNet and EfficientNets. And what they found is that what is it that we find? That in almost all data, in fact, every data set, visual transformer beats CNN. Do you see that? That's when you realize it's a moment. Something really big happened. Go ahead.
The market, like, are we using CNN or using transformer?
Today, both are in heavy use. Though more and more, the transformers are dominating. But there are many situations. Remember the no free lunch theorem. So there are situations where CNN still outdo. It's also the cost of CNN is much smaller. Transformers are very expensive. Yeah. Okay. So look at your problem, see if you need it, see what works. Always experiment. And these days, experimentation has become so easy. Download models from Hugging Face. Out of the box, compare their performance, then fine tune and then compare their performance. Right? So what you notice is that when you have results like this, and your model does so extraordinarily well, you know you're looking at something good, right? So now, like in hindsight, we may say, wow, well, it was perhaps obvious. Transformers are taking over the world. Back then, it was not so obvious. CNNs were dominant. They were absolutely dominant. They had no problems. Like, for example, with RNN, at least he had a problem that the whole thing was sequential. And you couldn't use the massively parallelized GPU hardware with them. You couldn't really make very deep networks with them. By CNN, I include LSTM, GRUs, all of this put together. But with CNN, there was no such problem. It was doing very well. People were making, by the time they reached inception, V2, etc., the things were going really well for the computer vision. So when, even for discriminated tasks like classification, these machines, this transformer-based approach immediately achieve state-of-the-art, that's when people realized, a couple of realizations dawned on people. First, they realized this. There's something deep about transformers that we don't quite understand. Right? We have built a machine whose full potential we haven't realized. We don't know why it works, but all we know is whatever problem we are throwing it at, it seems to go and achieve the state-of-the-art in it. So look at this attention. If you please pay attention to this picture, just the first picture. If you're trying to tell what animal it is, just look at that attention map. Would you agree that it is doing an amazing job at immediately picking up where to pay attention and deciding what is it looking at? Yeah. You see that, right? Just amazing, right? It does that. Likewise for aeroplane. Aeroplane is going through the cloud. This is a tough image. You know, there's white in the sky, white in the aeroplane. And guess what it does? The machine simply gets rid of the cloud. Practically, right? Do you notice that? It says cloud, no cloud, forget it. Here is the aeroplane. I know. Right? And look at this picture. Again, there's a lot of confusing details. Right? And the machine tends to pick it up, and there's more to it. There's a lot. So this paper was a very simple paper, but a very influential paper. You realize that, right? It takes this idea, can we use transformers for vision? And then how do we do that? And figures out by using a simple patching strategy. And then realizes that, hey, I have a visual vocabulary of sorts, right? Don't really need a vocabulary, but I can get away with it. And when you do that, and you can see different, but look at this, guys. By now, I hope these equations look very straightforward to you. These are your standard transformer equations. Yeah? Nothing should be surprising to you at this point. KQV, what are those KQVs? Query key values, right? And attention score is the softmax of Q in a product of KQ. And what is that wiggly square root of DH? It's just a normalizing factor to prevent the numbers from blowing up. It helps in stabilizing the computes, that's all. And then multi-head attention is just concatenating them and finally doing one more projection transform to produce the output. We have done all of that. So by now you see these equations and you notice that after a little while, people don't mention these equations because they have become so well known in the field that people don't bother mentioning it. And these machines do very well. I won't go more and more into it, but that is the VIT, visual transformer. This paper introduced the concept, therefore, of visual. So now there's more to it. Is there anything significant? Anyway, you can pay attention to this and you can see where is it paying, or what is the real attention map? Because when you look at some model's attention map, it tells you what is it that you're looking at. I believe this is a fish. 93 is a fish in an aquarium. And it seems to have zeroed onto the fish to tell what it is, isn't it? And
It has really like multi-attention, the horse and the background, power line.
power line, yeah. So this is it, guys. Read this paper. Can I please expect you to just read through this paper? Would you guys feel it's easy paper, right? After that, the key idea was this: slicing it up to create words or tokens.
Only one question for this. For example, if we could understand this with our English like 36 or tokens, which is our word embeddings, and then we drive the KQ.
Yeah.
So similar to this for the images, has there been some kind of a chart that we this or everything is happening at once?
No, you don't care because see, 16 by 16 is just 256 times 255 is your total vocabulary size, but you don't bother converting it to token ID or anything. You directly linearize it, make it into an embedding vector and put it, pass it forward. So the only thing, see, if you think about it, I said that, okay, let's go back and see. Let's go back. See, all I'm saying is, think about it. Any matrix will do the projection for you. So after you have flattened out the image into a vector, you are just multiplying it with this matrix. So the only learnable thing left behind is to learn the weights of this matrix, the values of the matrix, isn't it? Let it learn through backpropagation. And so you don't have to do that funny thing of looking up a dictionary that you do with Word. In some sense, it's simpler, isn't it? You just flatten the image, the patch, and feed it into the matrix. Out comes the embedding vector. As simple as that. Right. So guys, I don't know if you realize all of neural networks, right, is the power of very elementary mathematics. Just linear algebra, some bit of calculus, and that's all it is. Yeah. And yet, it is like working miracles. Yeah. So just on a lighter note, I'll mention to you, the people in computer, so I come from a computer vision background, right? So in the computer vision, there are elegant theories. If you read computer vision textbook, there are lots of fascinating things, exotic animals in the zoo. And very well argued mathematics and so forth. And then when people started seeing all these CNNs and VITs doing so well, they looked at the theory of it. And the theory looks so simple, they say, disgusting and barbaric. Right? Like, it is just not fair that it's working so well. You can imagine, right? In terms of well-argued, elegant theories. Now here comes this simple concepts, and it takes away the cake, like, you know. But that's sort of some of the feeling people had in the community when you started seeing computer vision being taken over. So many aspects of computer vision being taken over by neural networks, so that, you know, people began to say, so our only job is to be the weaver. We sit down and wire and rewire networks, and that's all we do. Right? Yeah.
So if I have both text and a picture,
Yeah.
and then I could go with the transformer approach. I'll pick a model for sentences like we've been doing.
Yeah,
Then another one for
images.
right?
I'm coming to that. That's all, multimodal.
But yeah, my question is, maybe you talk about it, but do we store it in the same vector database?
Yes, you do. In fact,
change
that is my next paper that I was going to read. It's 4 o'clock now. I think I would like to have some demo. So here's the thing, guys. I've read 2 research papers, explained it to you. If you feel that enough of learning, then we should move to demos. People have done some work and then to the Cambrian explosion. If you have the appetite for one more, then I'll come to exactly that. The beginnings of multimodal. How do you understand text and images jointly together? Yeah. We could do that. But this paper, guys, does it feel good? Oh, by the way, this paragraph is worth reading. Let me read this paragraph since it just caught my attention. We note that visual transformer has much less image-specific inductive bias than CNN. What does that cryptic statement mean? Would somebody like to enlighten me?
There is no way of looking at the basics of this.
Yes, those real-life characteristics are not baked into the transformer way of thinking. Nevertheless, it seems to perform well. Like it seems, why? Why? Right. It's a and yet it does well. So the only thing, you remember, we put a lot of emphasis on translation equivariance, right? That if the subject moves from here to here in the image, the representation moves from here to here. Yeah. Think of Plato's cave. So like that. But it doesn't seem to, the only place it happens are the MLP layers, which are essentially, people look at it as dumb layers. Well, not dumb layers, but okay, simple feed-forward layers. Also, the two-dimensional neighborhood structure is used very sparingly. So now there have been subsequent work that tried to look at the hierarchical aspect of the features. For example, the Swin transformer is an approach that actually brings about a little bit of the hierarchical approach. Now, I'm not going to read the Swin transformer paper. It's a little bit, can take up time. Yeah.
So very interesting. If I could relate that to the normal transform, the visual transformer, and indirectly here, the transformer is already doing that perturbation, all the things. It's learning by itself.
Learning by itself, yes.
By learning. So they're not explicitly.
Yes.
So I tend to think that this is more intelligent than the CNN. CNN, because you're force feeding in a way. I can put it that way.
Yeah, it is there. See, the way here are people, there are various camps of people. There are many people who still believe CNN is the way to go. It's fast, it's efficient, it is intuitive. You can make head and tail out of it. Then there are people who believe that transformers, for reasons, we don't fully understand how transformers work and think, but for some reason they think deeper. They reason in a much deeper way. So they're both sides. And as this paper then goes on to say, an alternative to raw image patches, the input sequence can be formed from feature maps of the CNN. You know, remember, what does a CNN produce? It produces the feature map. So one question you can say is, okay, what about this? Don't feed this transformer the initial picture. Yeah. Pass it through a few layers of the CNN and then do it, right? I don't think they did the experiment themselves. As a special case can have, which means that the input sequence, flattening the dimension, classification. I don't think those experiments are here, but they must have been done. People must have tried it. But anyway, this is your VIT. So guys, what would you like to do? I would like to do presentations. And after that, time permitting, would you like to have one more paper? Multimodal learning, or keep it for next time? How many for next time? More papers? Okay, most of you are saying next time. What's that?
Attention is all that matters.
Attention
is all that we do.
Attention is the out. Right. Okay, guys. So these two papers, can I expect you to please go and review these two papers? Now, can I start, guys? We are 6 weeks into this course now. You think you have enough familiarity with transformers that I can start releasing quizzes on encoder, decoder, self-attention? One more week before I start releasing quizzes. Okay, I'll wait a week because then there'll be a whole barrage of quizzes I can release. It will just be for you to reinforce your own learning. Nobody looks at the quiz course except you, right? And you can keep taking the quizzes over and over again. I know people who come back and take the quiz all over again 1 year later.
When you split into transformer, like this is the board like
Yeah. Yeah.
So, but you mentioned that in general, like never be the plants. The EVs are they going to use? There is nothing in it. Right? So
Yeah, see, this is a very good question, Dhaman, that you brought. In thoughts, you would rather that your chunk captured a thought, a sentence was full. In images, if you just do rigid 16 by 16, are you not being inefficient where you are cutting it off? And that is the sort of issues being addressed by the Swin transformer paper. I've given it to you as a reading exercise. Oh, sorry, I just managed to kill that. So guys, before you go, just hold on a minute. In the visual language, I've given you guys 2 papers to read on your own. Study the Swin transformer and the TNT paper. These are reading assignments, guys. The homework assignment, I'll add to this. Right? That also I'll add to this.
You may want to pause the recording.